Hello, in this topic we will discuss about graph theory, and here you can see a map of the whole graph theory that you have to know. I want you to show the map basically because I want you to see that all the basic elements are connected with these two things here in the center of the graph of the presentation. So let's focus in these two things, trail and path, to explain them, and then you can see how everything is connected, how circuit, cycle, Eulerian trail, Eulerian circuit, Hamiltonian path, how all of them they are connected with these two. Now let's see it more in detail. Now, basic things. I have a graph which consists of vertices A, D, C, B, E, and edges, as you can see, AD, DC, CB, and so on, EB. Now, what is a walk? A walk is a sequence of vertices, but adjacent vertices. What does that mean? I'll give an example. Let's see that A, B, C, this one here, A, B, B, C, it's a walk. Another walk could be A, B, C, again B, I'll go back, E here, and D. This is a walk. It's a sequence of vertices. There's no limitation how I can move. But let's see this one. Let's see B, A, C. From B I go to A, and then I have to go to C. But you see, I cannot go to C. There is no edge that connects A to C. There's no C is not adjacent to A, so this is not a walk. So basically, if I don't have a walk, I cannot have anything of the other things, because everything is connected with the walk. Now, what is a trail? A trail is a walk, vertices, adjacent vertices, where no edge is repeated. Let's see it here. So for my trail here, I have to find adjacent vertices where the basic no edge is repeated. So basically I can have a trail where from A, B, C. A, B, C, it's a trail. Another one, A, D, C, A, D, C, B, E, D. I didn't repeat any edge, so this is a trail. Be careful. No edge is repeated. It doesn't say about the vertices, so I care only about the edges. So in my trail, I can repeat vertices. Now, let's see the path. What is a path? A path again is a walk where no edge or vertex is repeated. Now, this generally is this is one of the difficult things that I can find in graphs, because I don't want an edge or a vertex to be repeated. Be careful, a single path like that, it's easy to find. For example, here I can go from A to B, A, B, B, C, A, B, C, D, and then E. Be careful, this is a path. If I will go back to B, it's not going to be a path. Why? Because I repeat the vertex B. Be careful, no edge or vertex is being repeated. Let's see now what extra I have. Now from trail, I'll go to circuit. What is a circuit? A circuit is a trail, meaning no edge repeated. I will have I'll go from vertex to vertex, but I will not repeat edges. So it's a trail that starts and finishes at the same vertex. So basically I have to start from one vertex and visit other vertices, but without repeating the edges. Be careful. So here, let me see if I have, let me copy also to have this. So let me have here a circuit. So I start from A, I'll go to B, to C, to D, and to A. This is a circuit. I started from a vertex, I visited my other vertices, I didn't repeat any edge, and then I end up to A again. Now, let's go further. A sub case of the circuit is a Eulerian circuit, which is what? It's a circuit, meaning I start and finish to the same vertex without repeating edges, but I have to traverse all the edges once. So here, in this circuit, you see I went to B, C, D, A. I didn't repeat any other vertex, edge, but now to make it Eulerian circuit, I have to include all the edges. So a Eulerian circuit would be let's say I start from A, B, C, D, then I'll go to E, then to B. Be careful, it doesn't say if I have to repeat vertices. I can repeat vertices, and then from B I can go to D, and then I can go back to A. So this is a Eulerian circuit. Now, what happens with the other case? Very often I cannot visit all the edges and then end up to the same, start from a specific vertex and end up to the same vertex. But I can do what? I can make a Eulerian trail, which is a trail that will visit all the edges, but it will finish to another vertex. It will not finish on the same vertex. So here, let me find a Eulerian, the graph that we have now, we cannot have a Eulerian circuit, a Eulerian trail. Now, to find a Eulerian trail, I have to make another graph, which could be something like this one. Let me see. Eulerian trail. So here I will start from B. I'll go to C. Remember, I want to visit all the edges, but not to end up to the beginning one. B, C, D. Then I can go to B again. Then I can go to A. And then I can go back to D. Now you see I visited all the edges, but I didn't end up to all the vertices, but I didn't end up to B. So this is a Eulerian trail. I hope this clarify more the things. So you see, already we saw that Eulerian trail is connected with the beginning of the trail. No edges repeating. And the circuit is again connected with the trail, but I want to start and finish at the same vertex. Now, last but not least, it's the cycle. Now, what is a cycle? A cycle is a circuit which is what? It's a trail which is what? It's a walk where I traverse no edges without repeating them. So it's a circuit that no vertex is repeated except the starting and the finish one. So if I'll go here to my graph and I want to find a cycle, where I will start? I'll start from A. Then I'll go to D, then I'll go to B, and then again to A, and that's a cycle. Of course I can find many cycles in a graph. Another cycle will be B, C, D, E, and then again B. I made a cycle. Be careful, I don't need to go to all vertices. So here my cycle is what? A circuit that no vertex is repeated excepting the starting and the finishing. Now, what is sub case of the cycle? I have a Hamiltonian cycle, which is what? It's the cycle that visits every vertex once except the starting and the finishing one. Now this as you will see, this narrows down my options. For example, here, if you will try, you will see that it's not able to find. It is not. We are not able to find a Hamiltonian path, a cycle. But here, I can start from Hamiltonian cycle. Here, be careful. I start from A. I go to B, then I'll go to C, then I'll go to D, and then A. I started from A, I end up to A, I visited all the vertices of the graph, and I end up to A. See that I didn't need to go to that DB edge, because I don't need to pass from all the edges, I just need to pass from all the vertices. That's the tricky part. So now, if I'll see here my whole graph, one thing is left only, and that's what? The Hamiltonian path. You see it's connected, Hamiltonian cycle, but I can have a Hamiltonian path. What's that? If I cannot have a cycle, I usually maybe I will be able to find the Hamiltonian path, which is what? It's a path, obviously, where no edge or vertex is repeated, but visits every vertex once, but without the start one and the finish. They don't need to start and finish at the same one. Now, this one we can find here, for example, in this graph, I can find a path. So if I'll start from A, Hamiltonian path, so if I'll start from A, I can go to D, then I can go to E, then I can go to B, and then finally I can go to C. So you see, I visited all my vertices, but I didn't end up to A. That's a Hamiltonian path. It's easy to be found in a graph. Now, to recap, if I want to visit vertices, I will have to be what I'm searching is a Hamiltonian path or a Hamiltonian cycle. If I want to visit edges, I'm searching basically for a Eulerian circuit or a Eulerian trail. That's what you have to remember. So the Eulerian trail and circuit is connected with edges, and the Hamiltonian path and cycle is connected with the vertices.